Okay, hello. We are in coding demos for Indiana State Computer Science, and we're looking at the halting problem. This is part 2, and there's a part 1 video that we'll have a link up here where we looked at what happens if we assume that the halting problem is decidable. So what is the halting problem, and what if we actually have a solution and we come up with the conclusion that it doesn't make sense, you get a contradiction. So it must be the case that you can't actually solve the halting problem. So what I want to do in this video is a reading of this proof in verse form in the style of Dr. Seuss by Jeffrey K. Pullum. So we'll leave the structure of the proof up here if you want to pause to remember basic steps here, and let's see if this properly follows that pattern. Okay. No general procedure for bug checks will do. Now, I won't just assert that. I'll prove it to you. I will prove that although you might work till you drop, you cannot tell if computation will stop. For imagine we have a procedure called P that for specified input permits you to see whether specified source code, with all of its faults, defines a routine that eventually halts. You feed in your program with suitable data, and P gets to work, and a little while later, in finite compute time, correctly infers whether infinite looping behavior occurs. If there will be no looping, then P prints out good. That means work on this input will halt, as it should. But if it detects an unstoppable loop, then P reports bad, which means you're in the soup. Well, the truth is that P cannot possibly be, because if you wrote it and gave it to me, I could use it to set up a logical bind that would shatter your reason and scramble your mind. Here's the trick that I'll use, and it's simple to do. I'll define a procedure, which I will call Q, that will use P's predictions of halting success to stir up a terrible logical mess. For a specified program, say A1 supplies, the first step of this program called Q I devise is to find out from P what's the right thing to say of the looping behavior of A run on A. If P's answer is bad, Q will suddenly stop. But otherwise, Q will go back to the top and start off again, looping endlessly back till the universe dies and turns frozen and black. And this program called Q would not stay on the shelf. I would ask it to forecast its run on itself. When it reads its own source code, just what will it do? What's the looping behavior of Q run on Q? If P warns of infinite loops, Q will quit. Yet P is supposed to speak truly of it. And if Q's going to quit, then P should say good, which makes Q start to loop. P denied that it would. No matter how P might perform on Q, Q will scoop it. Q uses P's output to make P look stupid. Whatever P says, it cannot predict Q. P is right when it's wrong, and is false when it's true. I've created a paradox, neat as can be, and simply by using your putative P, when you posited P, you stepped into a snare. Your assumption has led you right into my lair. So where can this argument possibly go? I don't have to tell you. I'm sure you must know. A reductio. There cannot possibly be a procedure that acts like the mythical P. You can never find general mechanical means for predicting the acts of computing machines. It's something that cannot be done. So we users must find our own bugs. Our computers are losers. The end. Okay, so what you might want to do is reason through this again, and then take out a piece of paper and see if you can write down the basic structure of the argument again. This is a pretty cool proof, and it's definitely one of your sort of top 10 proofs related to computer science. Okay, the end.